And this is a real life problem. So what we do is we take 2 ice cubes. So here's our ice cubes, and our ice cubes are at -11 degrees Celsius. And these ice cubes are placed into 215 grams of water, and that water is at 25 degrees Celsius. So the question is, what is the final temperature after all of the ice has melted? Okay, so basically our water here is 25 degrees Celsius, and we have 215 grams of that water. Now we have our ice cubes, they're 20 grams. And I assume both ice cubes are 20 grams. So we have a total of 40 grams of ice. And those ice cubes are -11 degrees Celsius. So since our water's hotter, the heat is going to flow from the water to the ice, right? Until that final temperature of the ice that started and the water is the same. Okay. And so when we talk about this mathematically, we say negative Q of the water is going to equal positive Q of the ice, right? So that heat is going to go to the ice. Now, the problem also gave us a few different tidbits of information that we'll use throughout the process. And so we have delta H of fusion. Okay, so what that is when we take our ice and we convert that to a liquid. Okay, so the heat of that process that's happening is a positive 6.01 kilojoules per mole. Okay, and so we're breaking these intermolecular forces, so our heat or our enthalpy is going to be positive. Okay, and then the last thing we have is specific heat values. So specific heat values of water as a solid is 2.09 joules per gram degree Celsius. Right, so that's how much heat the solid water can absorb per gram, and to increase 1 degree Celsius. And then also we have the specific heat of the liquid water. That's 4.18 joules per gram degree Celsius. Okay, so that's all the information that we're given in our problem. And so we have to kind of think about what actually is happening in the system so that we can mathematically tackle this problem. Okay, and so I have put it all on this graph for us. So we have our water up here, 215 grams of water, and it's going to start right up here at the temperature of 25 degrees. And we have our ice down here at -11 degrees, and we have 2 of those ice cubes. So that's 40 grams of ice. Now we're going to take that, and we have to heat our ice, right? So as we're heating the ice, we have to go from the temperature of -11 degrees to 0 degrees. Okay, so there's heat that's going to be associated with this step. So we'll just call this kind of Q1. This is our first step. The next step is we have to convert all of this ice to water. Okay, and we're going to use the delta H of fusion here. And remember, the temperature doesn't change, so we're staying at 0 degrees Celsius. But we need to figure out how much heat it's going to require to get the ice to the water. Okay, so here's our step number 2. The next thing is we have to figure out how much heat in steps 1 and steps 2 is required that our water has to give, right? So step 3 is the amount of heat that needs to be given. So that's going to lower this temperature by a little bit. Okay, now that we've lowered this temperature a little bit, our 4th step is to figure out what that distance is, or that difference in this range. Okay, so I know my temperature is going to end up somewhere in this area, my final temperature, as long as I have enough water that can melt this ice fully. Now, if I had too much ice, this water is going to freeze, right? But for now, I'm going to say, okay, my temperature, my final temperature is going to be in this range based on this idea. Okay, so we're going to go through steps 1, step 2, step 3, and step 4. I'm going to just kind of talk through the steps, how we're going to solve it, and then I'm going to actually solve it towards the end of the video. Okay, so the first thing we're going to do is to calculate the heat from ice, okay? And that's the heat needed to go from -11 degrees Celsius to 0 degrees Celsius, okay? Now remember this general heat equation, right? So Q is the amount of heat that equals M, or the mass of the ice. This is going to be in grams. CS, the specific heat of ice, times delta T. And remember, whenever we're talking about changes or delta T's in chemistry, we're always going to do T final minus T initial. Okay, so what this step talks about is this first part where we're taking the ice and changing the temperature from -11 up to 0 degrees Celsius, right? So there's mathematically how we deal with how much heat needs to be absorbed by the ice to change temperatures. Okay, so there's step one. Step two, we need to calculate the heat to actually melt the ice, right? So right here is this step. How much heat is it going to take for all of my ice, so my water as a solid, to convert to water as a liquid, right? How much heat is that going to require? And that's going to be dependent on how many grams I have. So I start with my 40 grams, and I'm going to use my delta H of fusion, because this is what that symbol stands for. Fusion is going from solid to liquid. And I know that if I have X amount of moles, or 1 mole, it's going to take 6.01 kilojoules. Okay, so this is step number 2. I'm finding out how much heat it takes to do this step. Okay, so then step number 3. Okay, and I kind of broke this off into 2 different sections. So calculate the total heat needed from water to heat the ice, right? So there was a specific amount of heat here in step 1. I guess it's for that area right there. There's a specific heat needed here in step 2, right? And all of that heat from step 1 and step 2 are needed to be pulled from the water, okay? And so this temperature is going to go down as the water gives the heat to the ice, okay? So my 1 and 2, we're going to add these together, and that's going to be how much heat the ice needs, okay? So this little negative sign right here says it's going to give heat to the ice, okay? So we've got ice on this side, we've got water on this side. So M is the mass of the water that we started off with, the specific heat of water, and again, that change of temperature. So change of temperature equals temperature final minus temperature initial. Okay, so I know my initial temperature, but I don't know that final temperature right here. How much, like as the water gives the heat to all the ice to get to this point, how much heat is that going to take? Okay, so this is the step number 3. Okay, and so that's how we're going to do it. Now, our last step, right? Our water's just given heat to the ice. So the ice is at this point, the water's at this point right here. And now what we have to do is figure out the final temperature as we go from these 2 spots. Okay. So I did the calculations earlier. The water is going to be at 9.12 degrees Celsius. The ice is going to be at 0 degrees Celsius, and we're going to find a number in the middle. Now, the way we do that is we set up this equation again. We have, and I called this the water versus the ice water, right? Because our ice is now water. Our negative sign tells us that the heat is going to go to the ice water, okay? And we have Q of the ice has to equal Q of the water. So how much heat goes down and how much heat goes up, we got to meet in the middle. So then we use the heat equations, right? So we have positive, the mass of the ice water times the specific heat of the ice water, which is now water, right? The change in temperature of the ice water equals negative, because the heat's going into the ice water, the mass of the water that we started with, the specific heat of the water, and the change in temperature of the water. Okay, so that's how we set up the problem. Now, again, you can pause the video here and see if you can, to solve those, solve them, we can get the same answer. If not, let's continue. And we're going to start right at the very beginning. So we're going to calculate the heat from the ice to go from negative 11 degrees Celsius to 0. That's our first step. The equation we're going to use is Q of the ice equals M of the ice times CS of the ice times delta T. Okay, and from the problem, I'm given the specific heat of the ice is 2.09 joules per grams degree Celsius. So when I look at this, right, we're going to calculate the heat. So we want to solve for Q of the ice. I'm going to look, the ice has a mass of 40 grams of ice. Okay, so 2 ice cubes that are 20 degrees Celsius is 40 grams of ice. The specific heat of the ice is 2.09 joules per gram degree Celsius. And I always write these up in a column so that I can make sure my units match. And that next we need delta T. To know this, we need the temperature of the final minus temperature of initial. Okay, so again, we're starting at negative 11 degrees Celsius and we're going to 0 degrees Celsius. So temperature final is 0 degrees Celsius. Temperature initial is negative 11 degrees Celsius. Okay, and we're solving for the heat. So here we've got grams, degrees Celsius, and our answer should be in joules. So now let's take our values and put them in our equation. So Q of the ice equals 40 grams times 2.09 joules per grams degrees Celsius times delta T. Delta T is final minus initial. So 0 degrees Celsius minus a negative 11 degrees Celsius. Okay, and I always tell my students, when you're using this, right, make sure your labels are the same. So every single number that we put into this equation has to do with the ice. So I'm not writing my labels out, but if it helps you, you could do that, right? Grams of ice, specific heat of ice, mass of ice. So now when I use my calculator, when I calculate those out, 40.0 grams times 2.08 joules per gram degree Celsius times a positive 11 degrees Celsius. Our grams are going to cancel with the grams. The degrees Celsius are going to cancel with these degrees Celsius. And we get 991.6 joules. Okay, so that's kind of our answer for number 1. So it's going to take this much heat to melt the ice. Amount of heat to melt the ice. Okay, so there's our step 1. Now our step number 2. Ooh, I lied, you guys. So this is the amount of heat to take the ice from negative 11 degrees to 0 degrees. I was getting ahead of myself, right? So first thing, we have to get that ice up to temperature, just like in the phase diagram. Okay, so now we're going to calculate the heat to actually melt the ice. Now to do this, we started with 40.0 grams of ice. And I want to find out how many joules of heat, right? Our last number was in joules, so I want to keep it consistent. So I'm going to find joules of heat. Okay, so now this problem becomes a stoichiometry problem. Okay, I know that I have a delta H of fusion, right? I have ice here, joules of heat. So I can use the delta H of fusion to go from moles of the water, right? Because we're going from ice to water. So we'll just call it the ice water like we did before, right? To joules of heat. So we're going to use that delta H of fusion. And then here we're going to go from grams to moles using the molar mass of water. Okay, so we've got a 1-2 step stoichiometry problem. Okay, so let's kind of write this out, right? So again, delta H of fusion goes with the reaction of H2O solid to H2O liquid, right? So we're going from ice to water, or that ice water, like I said, and then how much heat the delta H of fusion is it going to take to do that? Okay, so when I'm setting up my stoichiometry, every time I have an arrow in my plan, I'm going to have a dimension. So I'm going to start off with what I have to calculate what I want. So I'm going to start here. I'm going to put 40.0 grams of ice. Okay, and that's H2O. So I look at my periodic table, I find my molar mass, and I have 18.01 grams of ice equals 1 mole of ice. Okay, so if you look here, I have one arrow, so one dimension or one conversion. Okay, when I use this, my grams of ice at the top is going to cancel with my grams of ice at the bottom, and I'm left with moles right here. Okay, so my next step is I'm going to use the delta H of fusion. Since I have moles of ice at the top, my moles go on the bottom. So I have 1 mole. We'll just call it ice again. And that equals a positive 6.01 kilojoules of heat. Okay, so I have a second step in my plan, so I should have a second dimension. My moles of ice cancel with my moles of ice, and I get kilojoules of heat. When I say cancel, you guys, what I mean is if I have moles on the top divided by mole, it's the same thing, so it equals 1. And so that's why I can say, oh, it's canceled. I'm just normalizing it, it becomes 1. So with this, I take and I multiply my numbers across, divide by my number at the bottom, and I get an answer that is, let me make sure I write it down right. Ooh, actually, well, okay. So here, right, this gives me kilojoules. I said I wanted joules. So you have to do one more dimension, one more step. We're going to go from kilojoules to joules. So I'm going to do that here. So I know that 1 kilojoule equals 1,000 joules. And now I can cancel my kilojoules. My answer is going to be in joules. And I get 13,348 joules. Okay, so this number right here is how much heat it takes to melt the ice. So Q to melt the ice. Okay, so far so good. So we have step 1 and step 2. Our next step is we need to calculate the total heat that's needed from the water, right? The water is going to give heat to the ice. And so we need to calculate that total heat that's needed to get the ice from -11 degrees to 0 degrees. Okay, so I'm going to put that step number 3 up here. So in step number 1, plus step number 2 will give us the total heat needed for ice to go from 11 degrees Celsius to 0 degrees Celsius, and then to go from a solid to a liquid, right? So step 1 is this top part, step 2 is that last part. So the heat that's needed from the water is going to equal Q1 plus Q2. So we take 919.6 joules. We're going to add 13,348.1 joules. Okay, so the total heat from the water is going to equal 14,267.7 joules. Okay, so that's my step here. So my water has to give the ice this much heat in order to go from a negative 11 degree solid to a 0 degree liquid. Okay, so we have that number, and now we can calculate this temperature of the water after giving the ice that heat. Okay, so total heat needed is going to equal negative mCs delta T. Okay, and the water is going to give the heat to the ice. This is my water. This is my ice. Okay. From step 3, the heat is 14,267.7 joules. The mass of the water is 215 grams. And that was given up here in the problem. The CS of the water is 14.8 joules per gram degree Celsius. And my delta T is the temperature final minus the temperature initial. So temperature initial is 25.0 degrees Celsius. And temperature of the final, we don't know. So we have to solve from that. So we have all of our information here, our heat from the ice going from negative 11 as a solid to an actual liquid. That's how much heat is needed for the process. We have our mass of our water, our specific heat of our water, and our change of temperature, right? And we have an initial temperature of 25 degrees Celsius. That temperature is going to go down in order to give the heat to that ice. Okay, so that's how the problem's set up. So now let's put our numbers into this equation. So we have a positive heat that's needed. That's going to be 14,267.7 joules. Our mass of the water is 215 grams. We're going to multiply that by the specific heat. And we're going to multiply that by our temperature final minus our initial temperature. Okay, and we're going to solve for this TF value right here. Okay, so, sometimes you can take and rearrange this equation first and then put the numbers in, but for this case with the TF, I just figure it's easier to do this way. Okay, so we're going to multiply across and distribute this, and it reduces down to 15.8 degrees Celsius minus 25 degrees Celsius, equals negative TF. Okay, so hopefully I did my math right in that case. So 15 minus 25 is a negative 9.12 degrees Celsius, and that is going to be our final temperature. And that's the final temperature of the water. Oh, whoops, sorry, that's a negative there, right? I missed my negative. So double check, make sure you're paying attention to your negatives. That's going to become positive. So positive 912 degrees Celsius, right? And the reason why I caught myself is because here my temperature starts at a positive 25 degrees. I know it's going to drop, but it's not going to drop below 0 degrees, right? Our water's at 0 degrees, or our ice is at 0 degrees. Our temperature for the water is 25. That's going to drop a little bit, but it's not going to go below 0, right? So just kind of double check your temperatures and your numbers as you go to make sure they mathematically and chemically make sense. So now our last step, right? We need to find that temperature at equilibrium. So I know what temperature my water starts out, right? The 9 degrees, I know the ice is now at 0 degrees, and now I've got to fill that gap and figure out what that final temperature is going to be. So I kind of divide this up, right? My ice water is colder, it's at 0 degrees. My water is at 9 degrees. And so the water is going to have to give heat to the ice. Okay, so I set this up and say Q of the ice water, so positive Q is going to equal negative Q of the water. So here's positive M CS delta T, all of that ice that's turned into water now, equals negative M CS delta T of the water, which decreased temperature a little bit. Okay, so let's write this out. So we have M of, so all this is going to be for the ice water. So we have M equals 40 grams. CS is going to equal 4.18 joules per gram degrees Celsius. Temperature final, we don't know. Temperature initial is going to be 0 degrees Celsius. Okay, and remember, the change in temperature is going to equal final minus initial. Right, so we need both of those. So next over here, we have our negative sign. Our mass of the water is 215 grams. The specific heat is 418 joules per grams degrees Celsius. Notice this number is the same, right? I switched it because now we're at the water phase. And because we're at the water phase or liquid, we have to use the 4.18 specific heat value. Okay. And now we have our change of heat, or our change of temperature, which is going to be temperature final minus temperature initial. My initial temperature is now 912 degrees Celsius, and my final temperature is what I'm going to find, right? So the water is going to give heat to the ice water, right? It's going to keep giving heat until those final temperatures are equal. So the final temperature of the ice water is going to equal the final temperature of the water. Okay, so let's put all those numbers in, right? We laid them out on the table, so let's put the numbers in. So we have a positive sign. The mass of the ice water is 40 grams. The specific heat is 4.18 joules per grams degrees Celsius. And the delta T is the final temperature minus the initial temperature. Okay, so that's going to equal negative, and now we're back onto the other side with just the water, of 215 grams times the specific heat, which is 4.18 joules per grams degrees Celsius, times delta T, which is temperature final, minus the initial temperature, which is 9.12 degrees Celsius. Okay, so now we can take, multiply these numbers together and then distribute them. Okay, and I get a positive 167.2 joules per degree Celsius, TF, and then all this is 0, equals negative 898.7 joules per gram degree Celsius, TF, plus 178.17 joules. Let me just double check and make sure. So joules per degree Celsius, this gram should be gone, right? As I multiply these two numbers together, the grams cancel, and I have joules per degree Celsius times TF. Okay, next I have my joules per degree Celsius. I multiply by this number. Now my degree Celsius cancels, and that number has joules, right? So that's kind of how you go through. Now I'm going to combine my like terms. Okay, so I'm getting my TFs on one side and my joules on the other. and I have a negative 1065.9 joules per degree Celsius TF equals negative 8,178.17 joules. Now I'm going to divide by this number to get TF by itself. And my final temperature is going to equal 7.67 degrees Celsius. Okay, using significant figures, it's probably like 7 total or 7.7. You can go back and double check all your significant figures for all your orders of operation. But this temperature makes sense, right? My water starts at 0, or my ice water starts at 0. My water starts at 9. I know my final temperature is going to be in between those two after it's melted. I have a lot more water than I have ice, so I expect this to go down a little bit and the water to come up much more. So this number makes sense.